Efendim? Günaydın. Estağfurullah. Hakan Bey şu anda dersteyim. 2 saat sonra görüşebilir miyiz? Tamam. Estağfurullah. Okay, everybody. So we will continue our discussion on the operating system introduction to operating systems. Let me minimize this and do this, and yeah, okay, good. So yesterday we were talking about, okay, let's remember what we were doing. We talked about general structure, general definition of the operating systems, then we looked at the history of the operating systems, and then we were looking at the hardware related stuff about operating systems. We talked about the CPU a little bit and a little bit memory. Now we are talking about the other devices that are connected to the the computer, and we talked about this. We talked about the memory, and these charts are nice. We said that, okay, and now we talked about this disks. Well, I mean, disks, they are not necessarily disks anymore. Maybe we can call them secondary storage units. Because I mean, the only reason why we are using disk is that they are large, they are cheap, and they don't lose their information when the power is off. Okay, like the SSDs, right? I mean, they are larger, they are cheaper than the memory. I mean, cheaper per bit that you store. They are slower too, and they don't lose their information when the power is off. So that's what we are saying by saying disk. So don't take disk as like literally this kind of a mechanical disk. Okay, when I say disk, take it as our secondary storage units. Okay, so everything is valid for secondary storage units here, other than the mechanical stuff. We keep our operating system on the disk, and we keep our applications on the disk. We keep our data on the disk, and the data storage. The other thing is, remember our memory. We said that memory is faster, but it is small. But I like to run 100 programs at the same time, like I am doing on this computer. But if you put all of them together, there is no way that I can fit them into my available memory. So I am going to keep some of them on the disk, okay, on my secondary storage. Whenever I need it, I need to load them back from the disk. And when I load them from the disk, I need to put something back to the disk. And so disks are also important to manage the memory too, because memory will never be enough for us to keep all that kind of data at the same time. So we will talk about these when we talk about the memory, virtual memory. So disks, I'm going to skip this one. Okay, let's talk about these I/O devices. Okay, so the I/O devices are input-output devices are structured like this. Let's go back to our simple but nice picture here. Can I find? Yeah, okay. So this is our system bus. Everybody is connected to the system bus, including the memory and the CPU. That's what we assume. These are our I/O devices actually. Okay, our monitor, our keyboard, our printer, our hard drive, our sound card, our mouse. They are all connected to the computer through a controller. Okay. There is a specialized device. Its name is controller. Controller is an electronic device. It knows how to manipulate these devices Okay, it knows how to manipulate these devices. By manipulate, I mean it knows the details of those devices. For example, this hard disk controller knows about everything, knows everything about this hard drive, including the mechanical heads and the movements and then everything. Okay, so it drives these I/O devices, and they provide an interface for us so that operating system can communicate with these devices. So as I mentioned before, for example, for the keyboard, this controller has some special memory locations, and I say that, okay, I know the address of that special memory location. I say that I am going to read, for example, I am going to read a byte from that memory location. That byte corresponds to the whatever keyboard button is pushed. Okay, so that's how I am communicating as an operating system. That's how I am communicating with this keyboard through this controller. Okay, so I need a software to know. I need some software to communicate with this keyboard through this controller, and that software needs to know the details about this controller. Okay, and that software is called device driver. Okay, it's a device driver. Device drivers are software, okay, and usually they are part of the operating system. Okay, the operating system, in order for our operating system to talk to the I/O devices, they call functions from this device driver, and device driver handles the rest. Usually, the device drivers are provided by the manufacturers of these hardware I/O devices. Okay, so when you buy a piece of hardware from somebody to put in your, can I help you?
Yes. Buradan şey alabiliyor muyuz? Tutor geldi mi bana hiç?
Seç hocam, ikisini iyilerini al götür, bak öndekileri iyi.
Söyledin mi sen bunu?
Yok, söylemedi, unuttum.
Arkadaşlar 102 ve 108 için tutor arıyoruz. Şartlarımız 102, 241 ve 222 derslerinden birinden veya fazlasından BA ve üstü almak. Şeye gelirseniz, tutorluk yaparsanız.
Hangi dersleri arıyorsun hocam? CSE?
CSE 102,
evet.
241 ve 222'den BA ve yukarı alanlar.
Bir dakika, hangi dersleri arıyorsun? 102 ve 108 arıyorsun değil mi?
İkisini arıyorum. Çoğunlukla 108 olacak.
Evet. Hangi? 102, 108, 241, bir de hangisiydi?
108 almıyoruz da 102, 140, 222.
222 derslerinin birinden BA almak yeterli,
evet.
Öyle mi?
Ondan sonra eğer şey yaparsanız, successfully dersi yaparsanız, tutorluk yaparsanız, Yusuf Hoca size bir harf...
We had some Erasmus students last week.
Yeah.
Do we have them here?
Oh yeah, sorry.
Erasmus students? They quit? They went?
That doesn't understand Turkish. Yok hocam öyle bir şey.
Onlardan yapalım ya, onlar C biliyorlar.
Biliyorlar mı?
Ha.
Bunlar bilmiyorlar mı?
Yok. Hani C dersi almışlar, biliyorlar.
Ha, tamam, olur. I am open to about 12-14 tutors.
12, 14.
12 to 14, yes. So we'll have,
okay.
For 108, we'll have about 8 or 9, and for 102,
okay.
4.
And when you do that, you are going to give them half a letter
yes.
upgrade, right?
Yes.
If it is above CB.
CB and above, yes.
CB and above. If your grade is greater than or equal to CB or above, it will be upgraded half a letter. So your CVB will be BB, BB will be BA, and AA will be AA. AA will be FF, so it is circular.
Unfortunately, if you are planning to get an AA here, don't come. So I mean,
no.
But at least
okay.
You are not going to get anything.
Just to make sure that I will not give anybody AA. So.
Okay. Oh yeah, that's another. Okay, thank you. Fridays in the morning. So 8:30 to 12:30. But you'll be attending only one half of it. So either 8:30 to 1030 or 1032 to upgrade. Okay.
Hocam Erasmus çocukları bul ya. Are our friends from Erasmus program, are they online? Are they watching us? Do I see them? Do I see their names? Where did they go? Anyway, okay. I'll talk to them later. Okay, so as I said before, these are the devices, and when you buy a device, okay, you connect it to the controller of that device on your computer, okay. But you need some software that knows the details of this controller and this device, right? And that software is called device driver. And usually the device drivers come with the device itself, okay. But nowadays the devices are kind of standard. When you buy a keyboard, it is a keyboard. Everybody knows how it works. I mean, of course, I don't know. Maybe you may not know. Most probably, but I mean, as an operating system designer, people knows about that. And the device drivers are kind of standard. Okay, the USB device drivers, but nevertheless, they are part of most of the time they are part of the operating system. Why? Because those device drivers need to access these special locations. Okay, so do you remember these locations? Very special locations, special addresses, or sometimes I need to execute some privileged instruction to access these locations. So these device drivers, most of the time, they need to be part of the operating system kernel, and they need to run in the kernel mode. Okay, and they say that most of the time these kind of operating systems crash. It crashes because of these device drivers. Because as I said, device drivers are written by third-party companies, and sometimes they don't follow the exact rules required by the operating system, and they cause crashes because they are running in the kernel mode. Okay, that's why Microsoft or Apple or whoever designs the operating system, they have a very strict set of rules for the device driver software developers. They say that you are going to do this, and do this, and do that, etc. If you don't follow those, you are going to crash the whole operating system. If the Windows operating system crashes, who would I take responsible for it? Of course, Microsoft. Microsoft says that it is the device driver, not me, but I say that, well, it is your responsibility to make sure that your device drivers work fine. Okay, so that's the real picture, device drivers and the controllers. Again, controllers are pieces of electronic devices, physical hardware, and device drivers are software. And device drivers are written by the manufacturers of those I/O devices. Okay. Good. Any questions? Nope. Let me move on then. Let me move on with these I/O devices. Again, I/O devices are controlled by the controllers. Okay. And the devices are very complicated, and the controller handles this complex. The device driver is a middle layer software, as I said before, by the manufacturers, usually by the manufacturers. Okay, let's look at some I/O methods. Okay, remember what I said. Suppose I am the operating system, and this is my bus, and this is my controller, and this is my I/O device. Let me make this controller a little bigger. This is my I/O device. I don't know whatever it is. This is my controller. This is my CPU, and this is. It is supposed to go that way. Did you guys sign it?
No.
Did you sign it? No. Okay, and this is my memory, and suppose I like to do some input-output on this device, whatever it is. There are a few methods. The simplest one is the busy waiting. Okay, busy waiting is this. Let's say this is my printer. This is a printer. Okay, as an operating system, to print a character on the printer, I put the ASCII code of that character in this special location in this controller. 65. Okay, yes.
Online class don't.
They don't hear me. Where is my, what happened? It looks like I am on. You guys don't hear me? Anybody?
Hocam, we can hear you, but we can't see the screen. Yeah, yes, now we see.
So, this, I mean, from the beginning of the class or just now? Do you see it?
We just see the screen.
Okay, sorry for the mess up. It's not my fault. I don't know why, but this thing, can I try something else? Why, I mean,
Hocam, there's about 1 minute lag between online and
I mean, these fast routers supposed to be doing a good job, but I cannot connect through them. Maybe can I try this? Just hang on a minute. I will try this. Let's see if it will make any difference. I hope it does. Oh, okay. Doing something. Okay. Okay. Now let me see if this will help.
it's live hocam.
Okay. Can you hear me and see me okay now?
Yes, we are okay, hocam.
Okay. Today, for some reason, it worked. Okay, good. I said that to be able to print something to the printer, I send this 65. It is the job of this controller and the printer to check this special location and print this on paper, and that's it. But as a CPU, okay, I like to, as operating system, sorry, I like to keep printing this until my page is over, right? So, but the printer is not fast enough to keep up with me. So what am I gonna do? I will check for another bit. If that bit is 1, that means that the printer is busy. I cannot print. Okay. If that bit is 0, that means that the printer is available. You can print another character, right? So without seeing that this bit is 0, I cannot print something new. I have to wait. So as I said, printers are millions of times slower than the CPUs and my operating system. So what am I going to do? One of the techniques is busy waiting. Okay, I wait. I keep checking in an infinite loop. Okay, I keep checking this bit. Okay, as long as it is 1, I keep running this empty loop. It calls busy waiting. So obviously it is very simple approach for I/O, but it wastes CPU time, valuable CPU time. And while I am doing this, nobody else can use the CPU. right? That's a bad thing. But if I am the only process on this computer, then doesn't make any sense. Doesn't make any difference actually if I wasted my CPU time or not wasted, because I am the only process. I am the only thing on this computer that is doing this, printing something to that printer. Well, maybe if I am not doing any multi-programming, this might be okay. But if I am doing multi-programming, more than one program, all the other programs are waiting for me to print something to the printer, and the printer is too slow and it's taking so much time. So that's called busy waiting. It works sometimes, but most of the time it is a waste of CPU time. We don't like it much. What is the simplest approach? If your computer is very, very simple computer, like an embedded computer, okay? Embedded computers are computers that are used for very specific purposes, and you don't accept general purpose jobs on the embedded computers. So maybe busy waiting is kind of an option. The alternative is interrupts. So I expect the system to be smarter, okay? So this is what I do. As the operating system, okay, ask the driver to get the data and process blocks. Okay, when the data is ready, an interrupt is generated and process starts again. So this is what I do. I put the 65 in here, okay, and I continue doing something else. I suspend this job. And whenever the printer is ready to print another character, this device controller causes an interrupt. That interrupt will be handled by the operating system, and operating system will realize that, okay, the printer is available. Whoever is using the printer will be unblocked, will be waken up, okay, and the process will continue. So I get the help from the hardware. I am using this interrupt mechanism. Okay, that's the interrupt-driven I/O. Okay, this is more popular. Obviously, it is not wasting much CPU time. It is not wasting much CPU time because whenever that I/O device is busy, I don't wait until it is ready. I just put that process on hold and keep doing something else. Okay, so when I say it doesn't waste that much CPU time, it wastes some time because setting up the interrupt, getting the interrupt back, handling it will take some CPU time too. And remember, whenever an interrupt occurs, it means that a context switch has to happen, and context switch is expensive. Okay, so sometimes they do this. I am going to wait for a few, maybe microseconds, for this I/O to happen. If it happens, then I will do the busy waiting, that I will be happy. But if it is taking longer than a few milliseconds, then no, I am not going to wait. I am going to block and use the interrupt mechanism, because busy waiting, well, we don't like it much, but it doesn't have any context switching in it, right? So which one is more expensive, context switching or busy waiting? It depends on how much you are going to wait. So those kind of decisions sometimes are made by the operating systems. The third one is the more advanced one. It is the direct memory access, okay, DMA. This is what you do. You just tell usually you do this with your hard drives or SSDs, okay? You set up a special device CPU DMA chip, direct memory access chip, okay? You simply tell that, okay, I need this much data from this location in this memory location. Whenever it is ready, just transfer it for me and let me know when it is done, okay? So basically DMA is a very simplified CPU, okay? Whenever this I/O data is ready, okay, it gets the data from the buffers of the controller and puts it in the memory location that I want, and causes an interrupt to tell me that the data that you want is ready. Okay, so it doesn't keep the CPU busy to transfer the data from this location to the memory. Okay, and it is a much smarter way of doing input-output direct memory access. Okay, so DMA chip is somewhere on the bus. DMA, it behaves like a very simplified CPU. Doesn't do much. All it does is transferring the data from this controller buffers to the memory or from memory to the controllers. Okay, and it is smart enough just for that. And whenever it is done, it causes an interrupt. Let the operating system know that the DMA is complete now. Okay, so with the interrupts, I can print one character at a time. Every time I have to use the CPU time. Every time I have to handle an interrupt. So context switching is expensive. With the DMA, you tell the DMA that, okay, this is your page. Print this out to the printer. The printer handles everything about this printing job. It takes the characters one by one to this printer. Since it's a simplified CPU, it has time to do that. I am not wasting any CPU time. Whenever it is done, okay, it tells the CPU, tells the operating system that the page that you sent me is now printed. Okay, so we will talk about this detail in more detail when we talk about the I/O devices in chapter number 5, maybe 4 or 5, maybe 5. Okay, yes.
Hocam, you said I/O drivers are like softwares.
I/O devices are like piece of software. Yeah.
Yeah. Why there is a special method for this? If they are like softwares.
You mean these are hardware methods. Okay, maybe I shouldn't say that. These are it is up to the driver to use any of them. Okay, so we are talking about what the driver is doing with the slide. Actually, this is how you communicate with the controller, either busy waiting, interrupts, or the DMA. Okay, so these are the techniques that you use in your drivers, which is a piece of software. Okay. Thank you. Did everybody sign this? Okay. Good. Thank you. Okay, let's move on with the I/O devices. Let's talk about this interrupt mechanism actually. What happens? Remember what I said about the interrupt? These are the stuff. Okay, so this is the steps in starting an I/O device and getting an interrupt. Number one, as a CPU, okay, I tell the disk controller that. Okay, I tell the disk controller by writing in special registers inside it, saying that I need 100 bytes of data starting from this cylinder and this sector, okay, and make it available. And the disk controller will put that data into this special buffer, okay. So everything inside this controller. I programmed it. I said that I need this much data starting at this cylinder and this sector. So I am giving it all the addresses. Okay. And all the data will be available inside this special buffer which is inside the controller. This is not part of the main memory. Okay. Whenever the data is ready from this drive, okay, this controller makes that data ready. It moves all the heads, it spins the disk, and it makes sure that everything is loaded nicely. Whenever it is ready, it tells the interrupt controller, which is a device connected to the bus, that the data is ready. Now you can interrupt the CPU. The disk controller doesn't directly interrupts the CPU because it is the job of the interrupt controller. Because interrupt controller is connected to all kind of devices, and it is responsible for managing all those interrupts. Okay, and there is a special line between the interrupt controller and the CPU. Okay, an interrupt controller just raises that line. It lets the CPU that an interrupt has occurred. Okay, so that will stop the CPU from whatever it is doing. And then the CPU says that what kind of interrupt has occurred. The interrupt controller communicates that information to the CPU, either through this bus or this bus. Now CPU has the information about the interrupt. Okay, CPU will know that it's a disk controller interrupt, it's a keyboard interrupt or mouse interrupt or the video device interrupt, etc. It knows it, okay? And once the CPU knows about that, it gives this information to the operating system. And operating system knows, okay, what caused the interrupt, okay, and it gets that information and it knows how to handle that interrupt, okay. Now the operating system has the control of the CPU. Previously, the CPU was running a regular program maybe, okay. And when this happened, now the operating system, it takes over the CPU and the whole system, and it is trying to handling it tries to handle this case. So this is the hardware side. Let's look at the software side, okay. When I am running an instruction, a regular instruction, I am adding two numbers, okay, and suddenly I get an interrupt from the interrupt controller. That will I don't have any choice. I have to stop. As a program, in fact, I don't know if interrupt happened or not. I was adding two numbers, then I was going to increment one of the registers, okay. I added two numbers. After I added these numbers, an interrupt occurred. That will directly put me into the kernel mode, okay. And as an operating system, I have to handle that interrupt. And while I am doing this, of course, I saved all of my data, my program counter, my program status word, and the register and everything. So this is kind of a context switch. I context switch to the operating system mode, or the kernel mode, or the privilege mode, whatever you like to call it, okay? And I get that data, what kind of interrupt I had. It said that interrupt number 17. So I get that number and I look that number up from this dispatch handler list. There is an interrupt handler function pointer list, and I find the correct slot in there, and I found the function pointer and I jump to that function. Now I am handling that interrupt. After I am done handling that interrupt as an operating system, I said that okay, I am done. I handled this interrupt, whatever it was. Maybe it was, okay, taking all this data and putting them into the, where is my memory? Let me add some memory to this one. Okay, this is my memory. As a CPU, I took all that data and put them in my memory one by one. And then I am done, and maybe I can continue with the next instruction now. Another context switch from the operating system context to the regular program context, and I have to save, as an operating system, I have to save my tables and etc. and load all that data for this case, for this program, and continue running whatever I wanted to run. Okay, this is how the interrupt thing works in terms of hardware handling of it and the software handling way of it. Okay. So interrupt means that operating system is taking over. Interrupt means that I am going into the kernel mode. This is a hardware interrupt. Okay, this is a hardware interrupt caused by an hardware item, and sometimes we have the software interrupts, right? System call is the software interrupt or the trapping to the kernel. Okay, software trap. When the instruction says that system call, okay, it's a software interrupt. Operating system takes over. The CPU goes into the kernel mode, and I do whatever the program asks me to do. I do it, and I come back. By the way, this return doesn't have to be this return doesn't have to return to the next instruction, because this was a process. Operating system might choose another process to start. Okay, operating system might say that, okay, I handled this interrupt, okay, but instead of returning back to this process, I am returning to some other process because that process needs CPU time now. Okay, so after that interrupt, you don't have to go back to the next instruction immediately. Well, I mean, one way or the other one, this next instruction will be executed, but it may not be just after handling the interrupt. Yes?
What if the hardware interrupt occurred during the software interrupt?
Well, I mean, hardware interrupt can occur during handling of another hardware interrupt too. Those are the complications, and you have to handle it. So those are complicated situations. I mean, Sometimes interrupts has priorities. You say that this is an important one. Whatever it is, you are going to handle it. Okay? So if I am handling a software interrupt, that is a system call, hardware interrupt occurs. Usually you don't delay the hardware interrupts because sometimes they are sensitive. You are going to get some data from the network and you don't have enough buffer space. You need to get the data, etc. So you interrupt, your operating system kernel mode can be interrupted by another hardware interrupt. Okay, so you may go back to the operating system after handling that more important interrupt. Okay, that's why you have this interrupt control thing. There is a special bit in the program status word. It is called disable interrupts. Okay, when you disable all the interrupts, no interrupt can occur. Okay, and you can do it in the privilege mode. And in that case, of course, whatever happens, you will not break whatever you are doing. Okay, and sometimes this is done. Sometimes there are very special instructions, 2, 3, 4, 5 instructions. You say that whatever happens, you need to execute these instructions one after the other one. I don't want any instructions between them for the synchronization, especially. In that case, you disable them. But for most of the other time, if an interrupt happens, somebody has to make a decision. Should I handle this one or should I wait? Okay, any other questions? Okay, I try to make it clear that I try to make the line between the software side of handling things and the hardware side of handling things clear, because this course is not about hardware. But without knowing hardware, operating system doesn't make much sense. I'm not trying to teach you hardware stuff, but we are just simply reviewing it. Okay, so we mostly deal with this side. But without knowing this doesn't make much sense. Okay, and this is the system call, software interrupt. This is hardware interrupt. This is the software interrupt. Okay, for the software interrupt, I gave you what was the example here. I think I gave you a disk controller example here, right? The disk drive loads it. Now I am going to give you this example. You remember this C function, right? Read this many bytes from this file descriptor into this buffer. This is a regular read function from your C. Okay, C programming language. You open a file, you get the file descriptor, and you read it, this many bytes into this buffer. So one way or the other, at the end, this will be handled by the operating system because you need to access the device controller of your disk drive. Okay, so how does it work? So let's see what happens. This is your program. Okay, number one. Where is my number one? Yeah, number one is here. So I did this. Read FD buffer and bytes. So when you make a function call, what would you do first? First, you put this, okay, you put this into the stack, and then you push this into the stack, and you push this into the stack. So I push 3 of them into the stack, right? So I put my parameters on the stack, and I call the function read. I just jumped to the beginning of the function read. Well, I didn't write read. Where is read? The read is implemented by the C input output library. Okay, so this is the beginning of the read function of C input output library. So I am still in the user mode. This is my program. This is a function that I have called from the C library, but this is still in the user mode. I am just using somebody's library, right? What does the library do? It just says that, okay, I'm going to read something from this location, etc. So it puts the code for reading in a register, okay, and it provides all this data to and it just says that system call, the instruction system call. SYS call. Okay. This instruction executed. Okay. As soon as this instruction is executed, it's a software trap. An interrupt occurred. Software interrupt occurred. So who's going to handle the interrupt? It is the kernel. It is the operating system. Now operating system has the control. Okay. My CPU is in the kernel mode, and I dispatch this system call. So what do you want? It is number, for example, 17. I don't know what is. Okay. Number 17 corresponds to reading data from the disk. Okay. It just looks up the function for that one, and it calls that function. That function uses this data. Okay. Which function descriptor, how many bytes, where to put them, okay, and it handles that using one of the methods that we talked about a few slides before. And when the data is ready, okay, when the data is ready, I wake up my waiting process saying that, okay, your data is ready now. When the data is ready, this function returns and it says that, okay, your data is ready. Okay. So my program is waiting between this 6 and 9, and I don't know how much time it waits. Sometimes it is fast if the data is available already in my cache, in my hard drive cache. Sometimes it is in the memory. Sometimes it might happen too, because if I loaded it before for some reason, the operating system is smart enough to give me directly from the cache. Sometimes it takes lots of time because the hard disk is busy. It is calibrating its heads. Sometimes it does that too. I don't know how long it takes to load this file, load this buffer of information, but all I know that when it is done, I will continue from this point, from 11. So this is what happens when a software interrupt occurs. Okay, both of them. Okay. Both of them handled by the operating system, and both of them goes into the kernel mode. Both of them requires context switching from the user mode to the kernel mode, and both of them are really costly actually, because you need to save lots of stuff. Okay. Good. So traps means software interrupt. Interrupts are hardware interrupts. Any questions? Good. As you see, CPU is shared by the programs. CPU is shared by the operating system. And operating system, when I am executing my statements, okay, one by one, I do this, do this, do this, do this. Operating system actually doesn't know what I am doing. Operating system is run whenever an interrupt occurs, hardware interrupt or a software interrupt occurs. If none of them occurs, then operating system simply is blocked, is waiting to be called by an interrupt. Okay, and my hardware makes sure that, okay, operating system will definitely be called once a while, because there is a timer interrupt. That timer interrupt happens 40 times a second maybe. So operating system is guaranteed to be called 40 times a second. So every time operating system runs, it makes sure that everything is running properly. Okay, it makes sure that the computer is up and etc. If this mechanism doesn't work, then the computer is crashed. Whole computer is crashed. Good. Okay, good. Let's move on with the buses. The picture that I showed you before, okay, it was a very simplistic one in terms of connection of the I/O devices, memory, and etc. In our current modern day computers, the bus structure, hardware architecture is a little bit different, more complicated, more efficient. And we are going to look at that, but before that I need to take some break. 15 minutes. Let's be here around 11:30. 31. Pencereleri açabilir miyiz arkadaşlar?
Ya proje dönemi. Yani hani fikir dönemi şey değil ama yoğunluğu var yani kafamda şeyleri yapıyorum.
hocam nerede?
Biz Emulation 2 yaptık sorumluluğunu.
Hayır. Untitled benim şeyim oğlum, telifi bende.
Ben yaptım, bir taraf ama.
Geç.
Hocam isim bulalım.
İkballi misin bu?
Ha. Tamam. Ben söyleyeyim, ben isim için elimden geleni yaptım. Kendi adımı bile ortaya koydum.
Yani İkbal Teç koymaya düşündük.
Hepinizin toplasak bir debug etmezsiniz.
İkbal ilk mi, İkbal Teç mi okunuyor?
Bilmem. Nasıl kusura doksun. Sonuçta isim yazıldığında sıkıntı olmuyor. Sen istediğin gibi okusun.
İstediği gibi okusun. Sonra İkbal Teç değil.
Hı.
Hocam gel. Üstünü sana dinleyelim.
Gerek var hocam. Hüseyin hocam oyun yap.
Oh.
Ne gelmiş? Bu safhada gidiyor abi. Netflix, Kariyer.net, diş hekimi hizmeti, psikolog hizmeti.
Evet, psikolog sürekli bir şeyler gönderiyor. İlgi istiyor.
Hazır mısınız hocam?
Hocam çok iyi olmuş. Oha.
Güzel.
Ben ne diyeceğim?
Piyano tarafı benziyor.
WASD ile de oynayabilirsiniz.
Ama dışarı çıkıyorum ölmüyorum.
Hayır şey, 3 noktadan dışarıdan mesela. Kamu dışarı çıkman lazım.
He.
Diğer türlü geçen tutuyor.
Öyle.
Bahsetme hocam.
Ama başka şey yapsana ya.
Mobil için geliştirilmiş ya hocam.
Ben de boşlukta yap.
Tamam canım, bu setup olsun.
İstersen mi koydun?
Yok sesler hazır yani.
Senin. Sadece biliyor musun? Engelden çıkıyor mu böyle?
Ya yok ya, that's project.
Hadi aha.
Geliştirmeyeceğim zaten ya. Binlerce kez yapılmıştır ama çok avlıyor.
Evet.
Çok da basit bir şey aslında var ya. Ben diyorum bu oyunda nasıl yaparız lan böyle.
Mobilde şey mi çıkıyor ekrana? Böyle sağa sola tıklayınca mı oluyor mobilde?
Mobil aynen sağa sola tıklayınca oluyor.
Tamam mı?
Mobil yapamadım ya. Dual bot olsun. Dual bot da olur mu? Compile edemedim artık ya. Ne? Yok kalk gibi. Python ne ya?
APK çevirmişsin. Başka bir şey yok mu ya? Araştıralım.
Yok şey işte, kendi şey var Bulldozer diye.
Tamam.
Onun denedim olmadı.
Al. Yani çünkü
Hata veriyor ya bir yerde. Sanırım bir şey unutuyorum.
birinin için sırf bunun için Linux indirmesi çok saçma olur. Her şeyi Windows'ta koyacağım sonuçta.
Yok ama buna Linux getiriyor.
Tamam da her şey APK, yani her şey yapıyorsa APK çevirmişsin Linux. Adam mesela hiç Linux kullanmadan bunu yapabilir sonuçta.
Şey diyor işte, Google Colab var biliyor musun? O şey gibi işte. Yani sana şey açıyor bir tane. Jupyter Notebook gibi bir şey açıyor. Linux makinede.
Tamam.
Ona koyduruyorsun işte şeyleri.
Yapmak da sanal makine almıyor mu işte uzaktan?
Aynen.
Ondan sonra onun compiling halini indiriyor.
İşte o da hata verdiği için.
O zaman
Ben
ikinci
Dota'da
soru.
bir şey unutuyorum galiba. Çünkü benim üzerinde tutorial'da mobile çevirmeyi göstermiyor.
Yani müzik tutuyor.
Ha? Sonsuzluğu koymadım ya.
Hiç böyle kadar gelmemişsin değil mi?
Hoca ya. Normalde skor vardır ne oluyor? Üşendim onu koyayım ya.
Kim
Sen bir şey koyacaksın ya.
Benim skorum kim yiyecek şimdi?
Ama sadece örnekti ya.
Adam rekor yaptı, rekora koşuyor.
Hiçbir şey de gelmiyor ama artık.
Ödül basit oyun.
Bir şeyler geldi de.
Evet, bari müzik çalsın. Yani müziği bir ruhu alsaydın.
Vay şey oldu ama çapraz oldu böyle.
Bir şey random ya.
Anladın mı? Sen
Evet.
zorlaştı gibi ama.
Yok.
Ama hala şey,
Tamam.
random diyeceğim, feature diyeceksin uçaklarına. Daha incelse falan böyle bir yerler. Nasıl bakalım
Yok
yani.
ya bunu geliştirmeye gerek yok. Daha güzel yapalım. Linkiyle. Bazen unuttum artık ya. Hocam valla çok high score'a girdim.
Neden sarıyor bu böyle? Gözüm alamıyor.
Böyle aynı 1000 tane vardı bundan şeyde bu böyle.
Her ileride reklam var. Her sol tarafında reklam.
Hatta şimdi bir ekran girdi.
Taşıma sürekli.
Benim oyun nasıl?
Sen bu kadar şey biliyor musun? Sesin projeyi bitirmiş.
Baran için bizden 3 kişi veririz sonra. Baran değil hocam takım olması için 3 kişi veririz, size 1 kişi alırız.
Bak ben söyleyeyim. Debug da Hüseyin'e verin, Baran'a alırım.
Lan debug'ı hatta vermeyiz.
Debug'la Hüseyin'i niye veriyoruz oğlum? Debug'ı da niye veriyoruz?
Baran direkt sana. Baran'ı tek mi gönderiyor? Hüseyin'e karşı kaçlar ama.
Debug almadığı için Messi ile Ronaldo'yu bir
Oğlum
yerde
bak
vermeyiz.
bizde 15 lira ama artı adamlar çok tecrübeli.
Olsun.
Artı çay kahve öyle.
Hocam güzel mi?
Kafa var, Baran var. Takım değil oğlum.
Hocam bir game over olsana bir müzikleri falan veriyorsun yani.
4 dakika falan çalıyor şarkı, sonra yok.
Ne dakika oğlum bir dakika.
Ama 4 dakika koymuşsun öyle sen benim bir zaman aldığım yok.
Kendi oyunu değil mi ya? Tutorial mu?
Evet, veriyorum bunları. Tamam, her şeyi ben yaptım.
Ben de zaman aldığım
Ben
her şey yok.
Ben de mühendislik evet.
Sağ olun.
Bunu tersine mi yapayım?
Kontrol yapacağım bunu işte.
Ümit de öğreneceğim şimdi. Ya bugün başlayacağım bir de. Sen şeyleri verme hocam, bana bir yapma.
Tamam aldık şeyi. Aldık infoyu.
O da olabilir, o da var.
20 kişi.
Arkayı orta kalak ya. Hocaya söyleyeyim.
Zaten arkayla ortak olsun. Belli bir noktada.
Ben şey yapmadım.
Hepimiz aynı yerde.
Harfle aynı sadece ben harfleri kullandım
Ben böyle vücuduk görmedim.
Hasan sarayı da öyle var.
Evet. Bir de para hocam o adam şey ya.
Normalde neyi parçalayacak? Normalde neyi parçalayacak?
Bir tane parça.
Kendi parasına her şeyi başlatmıyoruz. Onu biz taşımayız.
Yok. Parası değil. Ben birkaç tane parçayı zevk almıyorum.
Ekmek
Bir taneden aldım. Diğer olmaz yani.
Ne gideceğim ben?
Yok, tatil. Ben de ikisi beraber yaptım.
Kariyer hedefim şu ya. Psikolog olayım.
İkbal tatili.
Bunu alabilirsin. Bir engel yok.
O kaldırıldı ya.
Nasıl kaldı?
Kaldırıldı.
Hocam baraj pahalı. Gidelim GKS'ye özel bir maaşın da olacak. Kredi çekersin.
Şey bitsinler. Benim için geçtiğine hiç bitmez.
Fazla ya. Oğlum kraldan çıkarılmış ya.
Tam böyle bir şey değil mi?
Çok işsiz var zaten. O yüzden böyle Ha şeye girmişler dediğini anladım. Tamam kendi.
Kodemini gören var mı? Ne o kodem? Okay, so as I said, the picture is not as simple as that, and more realistic picture. Well, this is a simplified picture too, but more realistic picture is like this. This is our CPU. We have more than one cores in it, and inside each core there is a level 1 cache. Then we have the level 2 shared cache. Then we have our GPU cores. GPUs are graphics processing units. Okay, and nowadays we use them a lot because, I mean, the name G is for graphics, but usually we don't use them for nowadays for graphics purposes. We use them for running, single instruction, multiple data. Okay, very simple instructions. Multiply this and this, add this value, and store the result back here. Okay, so these kind of instructions are very useful if you run them in parallel. For example, if you have two pictures, okay, picture means that two-dimensional data. Okay, if this is a 1000 by 1000 image and 1000 by 1000 image, if I like to add them together, how would you add them? Okay, you add each element one by one. Okay, so instead of doing this with a CPU, you do it with a graphics processing unit, Inside the graphic processing unit, there are thousands of cores, okay? So it can run the same instruction 1,000 times in parallel on different data. So you are running the same instruction on different data. Single instruction, multiple data, that's what it means. So we are using those GPUs for those kind of purposes, and nowadays they are very, very popular, especially with the popularity of these deep learning algorithms and etc. Or the cryptocurrency stuff. They are using these GPUs a lot, and they decided that since we are communicating with this CPU like memory, then maybe you should make this GPU part of the CPU itself. So we have the GPU cores, and we have our memory controller. See, this memory controller is a device that communicates with the memory itself. Okay, it's like a mouse controller, keyboard controller, USB controller. That's a memory controller, and your memories are connected to this memory controller. Okay, so there is a special bus. There is a special bus for connecting to your memory. Okay, and also there is a special bus to connect to your graphics card, so that you can show 200 frames per second at very, very high resolution. Okay, otherwise you will keep your main system bus busy for the graphics. Okay, and then there is this bus. Okay, DMI, direct media interface bus that will connect you to the platform controller hub. At this hub, you connect all of your other devices using the PCIe slots. Okay, this is the hard disk your disk interface, your USB 2 or USB 3 ports, your gigabit interface, and etc. They are all connected to this platform. We are going to see a more detailed version of this picture when we look at the I/O devices more in detail in chapter number 5. Okay. So as you see, there are very specialized buses for the memory, buses for the graphics card, buses for the other devices, and this is how the current computer architecture works. We will not go into details of any of them, but just to give you a more realistic picture. So our assumptions will be always we have a system bus, and all the controllers are connected to the system bus, including the memory controller and I/O devices controller, and we run our device drivers to control those controllers. Okay, good. So did I miss anything on this one? So main bus is the PCIe, Peripheral Component Interface Express bus. Very fast bus, but if you connect many of them at the same PCIe bus, then things will get slower. So we have a dedicated PCIe bus for the GPU, for the graphics card, etc. Okay, good. Special kinds of memory, DDR3, okay, they need their own buses, their special buses. Most of the CPUs, they support these kind of buses. Good, I talked about this, I guess. USB bus, maybe I shouldn't talk much about these now because I will talk about them. This interface, this SCSI, bus, it used to be very popular. Okay, it's a very old standard actually. Nowadays, our even simplest buses, the USB serial buses, is faster than that, but SCSI used to be the king of the fast I/O device bus standards. Good. So let's talk about this booting the computer. When the computer starts, what happens? Because this will be important to understand the function of the operating system actually. Okay. Actually, the first thing that works on your computer when it is booted up is the basic input-output system, BIOS. Okay, BIOS is on a chip, on a ROM chip, read-only memory chip. It is already on your computer. When your computer is turned on, okay, BIOS is a program. Obviously, it controls the whole computer. So it is a very basic operating system, if you like to call it that way. Okay, so its task is not to do multiprocessing. It is not. Its task is not to do interaction with the user, producing graphics and producing sound and etc. No, its task is just to safely check if the computer is okay. Then after that, safely load the operating system. Okay, it's called basic input-output system. It first checks to see how much RAM I have. Then it checks what kind of output devices, input-output devices I have, and etc. Okay, and the keyboard and other. That's it. And it scans all the buses to see what kind of devices are connected to those buses. Okay, and then it says that now I need to load the real operating system. Since I checked everything, okay, it knows how to check all of that kind of stuff, and it's going to boot the computer using the real operating system, and it's going to give all that kind of information. I have this much RAM, I have this many I/O controller devices, I have these and these and these kind of resources, and it's going to give all that information to the new operating system. Okay, so it will determine the boot device. Where is the operating system loaded? Is it on the disk? It is on the USB. Am I going to load the operating system from the network? It makes that decision, okay? And let's say it saw that the operating system has to be loaded from the, let's say, drive C for the Windows operating system, okay? It goes to that drive, and it loads the first sector, if this is a disk, okay, at the outer edge of the disk, there is a special sector, okay? It loads that special sector as an operating system, and it runs that program. Once that program starts running, it is the operating system. It does whatever it wants, okay? Operating system continues to load its parts. It says, okay, I'm going to load the scheduler, I'm going to load the file system, I'm going to load this security system, etc. Okay, so that's how the booting the computer works actually. So somebody has to start. It is the BIOS usually. Nowadays we have, instead of BIOS, we have UEFI system instead of BIOS. It does the same thing. It is only secure, faster, support more hardware, etc. But usually we call them BIOS. Okay, basic input-output system stuff.
Yeah.
Yes.
It could be more than one BIOS in a device.
Can you have more than one BIOS in
No,
it?
but it could be.
You mean in UEFI?
Yeah, or BIOS.
Well, I am not sure. I don't know. I never heard of it. Well, it could be why. Why do you need more than one BIOS?
Because if we have more than one BIOS, maybe having more than one BIOS solves another problem. I just wonder.
Well, I mean, a single BIOS should be able to handle all the hardware on your computer. I mean, it is usual to have more than one operating system installed on the same computer, and it would be the responsibility of the BIOS to choose which one to boot. They usually ask you as a user to ask you which one should I boot. There are 3 operating systems available, but more than one BIOS, I don't want to say no. Maybe there is, but I don't see any reason for that.
Hocam, I think in the passing from BIOS to UEFI, the computers has both BIOS and UEFI, and you can choose between them.
Okay, you want to do it with the old way or the new way? It's the same thing actually, but I mean, but more than one BIOS or more than one UEFI, I don't know. I mean, as I said, I don't want to say no, but I don't see the reason. Okay, so the basic thing is that somebody has to load the operating system. What did we say? Operating system is a piece of software. It has to be loaded to the computer and it has to run. Okay, and we are saying that BIOS is responsible, basically, for that task. And what does this make the BIOS? BIOS is the first operating system loaded to the computer. Very, very simplified, very, very primitive operating system. Its task is just to check if the hardware is okay, what kind of hardware I have, and the ultimate task is to load the real operating system. That's it. Okay. Good. So I think we will talk about this booting the operating system later during the semester again. So I am done with talking about the hardware. Let's talk more about operating systems now. We are going to look at the types of the operating systems. Okay, so these are the basic types. We'll talk about the mainframe operating system, servers, multiprocessor, personal computers, and etc. And you will see that some operating systems can behave like a mainframe operating system, server operating system, microprocessor, multiprocessing operating system, etc. So I mean, you cannot say that Linux is a server operating system or the personal computer operating system. If you configure it differently, okay, Linux can behave different kind of operating system. Okay, so the name doesn't imply what kind of operating system it is. It is the task of the thing. Okay, let's look at this mainframe operating system. Okay, we talked about the mainframes of 1960s, 50s, 70s. They are still available. Okay, they are very large. They are room sized, and they cost some of them they cost millions of dollars really. Okay, and they have very large capacities of CPU power and storage capacity, thousands of disks, whether mechanical disk or the SSDs. Okay, and sometimes some of them have thousands of CPUs on them installed. And usually ordinary users don't use these kind of computers. They are used for batch processing or transaction processing and sometimes time sharing. A batch system is this. You have a you have a system without any user interaction. For example, calculation of something complicated. Simulation stuff. For example, you designed a new airplane for 300 people, and you need to run the simulations for that airplane to see what kind of air resistance you are going to get under this and this circumstances. Okay, so very detailed CPU intensive stuff. You don't need any user interaction. So you run this system on this 1,000 CPUs for 5 days, and after that you get your results. It's a batch system. Okay. Obviously you need lots of CPU power, lots of memory, and these kind of mainframes, they offer you these kind of environments. That's a batch system. Or transaction processing system. You do the same thing over and over again. Banks do that. Okay, let's say the banks, they need to calculate the overall balance of people after the interests are added to their customers. So they have maybe millions of customers, and they need to do this processing for each customer one by one, and they are doing this without any user interaction. Okay, so check processing, or for example airline reservations, they are doing the same thing too. So these mainframe computers, they have large amounts of power in terms of CPU power or the memory or the storage, and they are very expensive. They are used for special purposes, and since they are expensive, our main motivation for this kind of operating system is the efficiency. Okay, you don't want to waste even a single CPU cycle for these machines because they are very expensive. You paid $2 million for this computer, and you don't want to keep it idle. Okay, so it has to be always busy doing something. What kind of operating systems we have? We have the Linux, we have the Unix variants of the for these kind of mainframe operating systems. Also, IBM has been a main player for the mainframe computers. OS 390 is an example system nowadays being used on mainframes. Okay, as you see, Linux can become a mainframe operating system. It is that robust. Okay, and the second type of operating system is server operating system. So what does a server do? Server waits for the request and it answers them. There are clients ask for something, server completes them and it says that I am done. Okay, what kind of services we have? Servers we have we have the file servers, we have the web servers, we have the print servers, and whatever you are running on these kind of servers are called the server operating systems. Okay, they could be very large personal computers, a PC, a workstation larger than that one, even mainframe computers. They can act like servers. So whatever you are running on these computers are called the server operating systems. Okay, so Windows has a special version for the Windows Server. It acts like a server, file server, or the email server, or the CPU server. Okay, some versions of Linux. This is another Unix variant, FreeBSD. Solaris is another Unix operating system. So these are the typical operating systems that act like servers. Okay. So a mainframe computer can act like if it is running a mainframe operating system, of course, a mainframe operating system, or a mainframe computer, very large computer, acting like a server, then it is running a server operating system. So there is no distinct, very black and white line that divides the. Okay, these are the server operating systems. These are the batch operating systems or mainframe operating systems. I can't say that. As I said, Linux is almost always will pop up as one example operating system almost for any of these classes. Okay, and multiprocessor operating systems. Well, nowadays you can't buy any CPU without a multi-core. Okay, even the simplest ones, they have more than one core. So then in that case, that means that even the simplest operating system is a multiprocessor operating system. Okay, so the many popular operating systems, including Windows and Linux, they run on multiprocessors. If the operating system knows that more than one core or CPU is available, okay, it should do the resource management accordingly. And Windows is doing a very good job about it. Linux is doing a very good job about it. I think I showed you yesterday how we are using those different CPUs. Okay, so this is the multiprocessor operating system. Then we have the personal computer operating systems. Again, the Linux is here. Our Windows 10, 11 is here. Then we have our handheld operating systems, smartphones. Okay, Apple's iOS, okay, or Google's Android. As you know, this is based on Linux again. So the main focus area of the personal computer operating systems is the interactivity, right? I mean, I should stay interactive with the user. The user should be happy. When they click on something, I should immediately show a response back. Otherwise, they don't like it. For handheld operating systems, again, interactivity is very important, but as important as the interactivity, it is the battery management. Okay, I cannot, just to stay interactive, I cannot use up all of my battery power for 2 hours and then I am done. No, my battery should last at least 10, 15, 18 hours. Otherwise, that handheld computer is not useful for me. Okay. Good. Then we have these specialized operating systems, embedded operating system. An embedded computer is this. Okay. They are specialized computers to control specialized devices. For example, on your TV, there is a specialized computer. It has a CPU, and there is an operating system running on it. Okay, so it is called an embedded. It is embedded computer and embedded operating system. Or your microwave oven. Okay, microwave oven has a specialized computer in it with the CPU and the RAM and the I/O devices and etc. And there is a special operating system for that one. These operating systems are special. Why? Well, first of all, the computer you put on them, these embedded devices, they don't have to be very powerful. Okay, I don't want to put a full-scale Intel CPU on a TV because that makes my TV much more expensive than it needs to be. So very special built CPU is put on it. It's a weak CPU, specialized CPU. So I need to take care of the CPU and the RAM, and the operating system is specialized for that one. For example, for these kind of computers, you don't need the protection. You don't need to say that, okay, I have two processes. You might have two processes. You don't have to say that this process number 1 cannot access the process number 2's memory space. Because both of the processes are your processes, you have written them. And embedded computers, you cannot install a third-party software on them, okay? So all the software comes from either from you or from your partners in software development. They are very carefully written, okay? So, well, protection is always nice. I mean, why shouldn't I protect my programs against others? But protection has a cost too, okay? So I don't want to get that whole cost. I say that, okay, there is no protection. Everybody can write to everywhere that they want. Everybody can access to any I/O device that they want. So it's like anarchy, but it is not actually, because, as I said, I don't run word processing on my microwave, right? It's a very simplified, special purpose computer, and that's why embedded operating systems are kind of light, and they have severe restrictions in terms of memory and in terms of CPU power, and the operating systems are specialized for these kind of computers. Again, Linux is here. Somebody modified Linux for the embedded Linux. Qnix or VxWorks are some popular embedded operating systems. And usually, since they are very resource intensive stuff in terms of the power levels of the CPUs and the memory and etc., usually people tend to write their software for these kind of operating systems in C programming language or in assembly, direct in assembly. Okay. Nowadays the picture is changing because even the CPUs for the embedded systems are getting much more powerful. They have multiple cores, and people started running their software in protected mode and etc. People, well, the picture is changing, but the main idea is the same. These computers. They don't have to be very powerful computers. And most of the time with the embedded operating systems, for example, for the TVs or the refrigerators or the microwaves, power management is not a big issue because you are directly connected. But there are some specialized embedded computers that run on battery power. But in that case, power is going to be important too. Then smaller computers, sensor node operating systems. Let's say I have a temperature sensor. I have many temperature sensors, and I distributed them in all rural areas of this part of Turkey. Okay, they are running on battery power maybe, and they are running on solar power, some of them. Okay, their task is to measure the temperature. They are sensors, right? And whenever the time comes, they just communicate with their servers to send that information. Okay, so each one is a real computer actually. They have a CPU, RAM and ROM, and they have one or more environmental sensors. Since they are computers, they run a very small operating system, very small operating system. And the task of that operating system, of course, managing the resources. Again, very small because I don't have much RAM, I don't have much CPU power. It has to be specialized. There is one example, Tiny OS is a well-known operating system for a sensor node. And they have severe restrictions on what kind of things get here run on it. But again, it's a specialized operating system. And you will not see the names of Windows or iOS on these kind of computers. As I said, they are very simplistic computers, yet they need some operating system on it. Then we have the real-time operating system. They could be very powerful, they could be very weak, but the main idea of the real-time operating system is this. Remember the interrupt handling routine that I showed you before? If I need some data from the disk, what do? I just call the read function, right? Read this data from disk to this buffer. That's what I say. but I don't know how much time it's going to take for me to get that data, right? It could be like in milliseconds, or it could be for 5 seconds, I don't know. Because it is not in my hands. I mean, this disk is a mechanical device. Things may get wrong with the disk, or there might be other processes using the hard drive. From time to time, my read-write heads, they need to be recalibrated. So they need to move the read-write head to the beginning and to the back and repeat this a few times, and etc. So the overall, in summary, I don't know how much time it's going to take for me to get that data. But if my task is very critical, for example, I am controlling a nuclear power plant, okay? I made a measurement, and I saw that the temperature from that measurement is kind of high, higher than I expected. Then I immediately need to run some kind of a action to lower that temperature, and this is time critical. I have to be responding in, let's say, 40 milliseconds, okay? But if I am doing this kind of stuff, if I like to read some data from the disk, and if I don't know if data is going to come in 1 second, 5 seconds, or 2 milliseconds, then I will be in trouble. Real-time operating system says that if you make a system call, I am going to give my answer in 10 milliseconds at most, okay? And I'm going to guarantee it. It will not take more than 10 milliseconds, okay? As a process, you will definitely have, okay, 30 times a second time, 30 times a second, and every time you are going to get maybe 10 milliseconds of CPU time. I'm going to guarantee that as an operating system. Well, in that case, I can control this nuclear power plant because I know that as a process, I know that whatever I wanted to do will be done in 10 milliseconds. Real-time operating systems are like that, and that's the whole purpose of it. Efficiency, they don't care. Power management, they don't care. Okay, CPU utilization, memory utilization, they don't care. All they care is meeting these real-time requirements. Okay. For example, your computer that controls your car brakes, when you press the brake pedal in your car, you expect your car to stop immediately, right? So there should be a real-time computer running to control your car brakes. Otherwise, if your computer says that I am going to load this data and it might take maybe a few minutes, a few seconds while you press your car, brake pedal, no, that will not work, okay? So for some critical cases, real-time operating systems are required. For some cases, soft real-time is okay. For example, as a media player, let's say I have a device, it shows video, okay? To show video means that I need to show my user 30 frames per second, 30 pictures per second. If I don't show 30 frames per second, video would not look very good. It is just laggy, it just looks flickery, and I don't like it. But from time to time, maybe every 10 minutes, if I skip a frame, and if I don't show 30 frames per second, maybe 25 frames per second, it doesn't look that good, but it is okay. From time to time, I can tolerate these kind of mistakes on soft real-time systems, okay? So usually multimedia systems are soft real-time systems. From time to time, I can tolerate these kind of errors. But for nuclear power plant or the computer that controls your satellite, okay, $10 million satellite, no, it has to be a real-time operating system. I cannot even once every 10 years, I should not be making these kind of errors. Okay. Good. So many embedded systems, handheld computers, most of them are soft real-time systems. Okay. So I like them to be real-time, but from time to time, you can violate some of these rules. Not much. Good. So these are the real-time operating systems. And then for the smallest ones, we have the smart card operating systems. Smart card are your credit cards. On your credit cards, you have the connections, right? You have the when you insert your credit card to the ATM device, or when you insert your credit card to the POS devices, okay, there is a computer on those cards. That's a real computer, okay. On your credit card, smart credit card, there is a computer. It has a CPU on it. It has some memory on them. As soon as you insert your credit card to the ATM device or the POS device, okay, your computer boots up, okay, operating system runs. Its main job is to verify the PIN number is okay, right? And then it communicates all that data. It makes sure that you are doing something right. Then when you pull it out, it just shuts down. So very small, very small computer, very small operating system running on it. Yet it's a computer and operating system. Okay, and they are called smart card operating systems. Obviously, I am not running Windows on them, right? Windows would be too big.
So
Yes.
Credit card has an operating system, so
Yeah. Your credit card has an operating system on it. And every time you use it, it boots up, it does something, and it shuts down.
it's not the ATM, it's the credit card.
What?
It's not the ATM, it's the credit card.
It is the credit card, yeah. Do you have a credit card with you?
Yeah, I
You see that those 6 connections on it?
don't see any.
Just turn on. No, I think that one is not a smart one, right? Does anybody have? Okay, show you.
I have
Smart. Maybe I should show you. Okay, smart cards. Those smart cards. Okay. Let me. Okay.
Credit cards really need a OS.
Just a minute.
Is a SIM
Okay,
card?
these are the smart cards, and these are the connection for the computer. I have 4, 8, 9 connections. When you insert them, it will boot up. And smart card computers. Let me show you the chip inside it. Where is my smart card CPU? I didn't write it right. Okay. So this is the smart card interface to the outside world. You have the ground. VCC is the power, so you provide power from here. And these are so this is the I/O. You are doing the serial I/O from there. So there is a computer, you are communicating with it. Okay? And if your card is expired, just break it. And under these pins, you are going to see the chip in it. Okay? It boots up. It does that. Even some of the wireless control system like our Gebze is not like that, but when you go under that checkpoint, that computer boots up from the electromagnetic waves. Okay, it communicates this data back to the receiver, and it shuts down. Okay, even some of those systems work like that. Yes.
Some credit cards have one job. Why they need operating system?
What is that job?
Taking money from us.
Well, I mean, there are very security related stuff in there. Okay, that's a very delicate job actually. Okay, so verification. I mean, it keeps the personal identification number in it. But if I take that computer, okay, and put it somewhere and try to hack it, it should not be recoverable easily, right? Okay, so if I keep that data very stupidly on a magnetic tape, like it used to be the magnetic tapes, right?
Yeah.
On it. So people used to copy those magnetic tapes in a very easy way, right? Now it's a computer. Even if you copy that computer, it's a computer. That encryption stuff doesn't work with the copy of the computer.
So,
Yes.
is it the reason how we can load money by using NFC?
While using what?
NFC.
How do you do that? I don't know.
Smartphones and NFC systems.
Well, I mean, smartphones are different. Okay, I mean,
But we can use smartphones to load the money to
your
our
credit card, really?
Yes.
I don't know. I didn't know. Well, can you? But how do you? Oh, wow! Because nowadays, yeah. Well, yeah. Those, yes. Those contactless credit cards, they boot up that way. Yes. Because you don't use touch these connections, that physical connections. You boot up your computer with a with a magnetic wave, and you communicate with the receiver there, and you provide all that information. But you do the security checks with the credit card, etc. Again, specialized computers, hardware is very amazing, but you have to run an operating system on that computer. Okay, that's a computer. That's a very small computer, and by the way, your SIM cards on your phones, they are computers too. Your SIM cards, they are smart cards, they are computers too, and they boot up every time you communicate with your SIM card. So actually, you are running a Java virtual machine on them. Okay. So the ROM on the smart card holds an interpreter for the Java virtual machine. Okay. As soon as you boot up, you communicate with the other party, and you load a special Java program and you run it. You give your results back, and it makes the security checks, and that works that way. Again, very small computer, and for the CPU time, it is important. RAM is important. Obviously, again, you are not going to run Windows on them. Okay, good. If there are no questions, it looks like I have a few minutes only. For the last part of the introduction chapter, okay, we will talk more about the operating system concepts. We will start from the processes, okay. This is about chapter number 2, chapter number 3, 4, 5, and basically it, okay. If you know about processes, if you know about memory, if you know about files, these 3 things, you know the operating systems, okay. That's what we are going to do. So before we start those chapters, these are just introductory information about the processes, address spaces, and files. And let's start from the processes. So what is the difference between a program and a process? Can anybody tell me? I'll say just the definition of process is there. Yeah?
Process is a running program.
Yeah, exactly. Process is a program, but it's a running program. What is the difference between a program and running program? In running program, you have your memory, right? You have your values for your memory. And if you think about the CPU, for a running program, you have your program counter. You have your program status word. You have your stack pointer, okay? You have your state of your whole program, okay? So process is basically a program in execution. We call it that way. And each process has its own address space. What's an address space? You say that you are a process, and you are allowed to access, okay, any value from the 000 to, let's say, just 64 kilobytes of data. You can do anything you want in this address space. This is your address space. You can do whatever you want. If you like to reach out of this address space, well, there is no way you can reach, because these are the only things that you can do. Okay, so this is the address space, list of memory locations from 0 to some maximum. And then, since I am a process, but I am a running program, okay, I need to have an entry in the process table. I am not the only process that is running on this computer, okay. In my process table, okay, I have many things. For example, my open files, okay. If I am blocked, my register set, okay, my register set has to be here. If I am blocked, I am not running, right? When the operating system lets me run again, it's going to load all of my registers from this table. What else? For example, I have how much memory I am using, how much CPU did I use. All these kind of information is kept inside this process table. Remember this one, I keep showing you the same thing over and over again. I will do the same thing again, okay? So this is a process, okay? All that information comes from the process table, okay? So when I run this task manager, okay, I get all that information from the process table. Where is, yeah, okay, maybe this one is a better one. Can I, how did I get the other view yesterday? There was this one. Do you guys remember? There was a view that I, by accident, there was a button somewhere here. There was a link. Performance. In the performance tab, yeah, it's the resource monitor. I opened it, and this is my resource monitor. Oh, this is for the resources. This is not the processes. Sorry, then let's look at the processes now. Okay, so these are my processes, and these are the information about my processes. Can I do this? Can I go there and get more information? Features of it? Where did it go?
So there was an option says go to details. I will select.
Okay, details. Do I see it? Is that, well, I think these are the details of each of the processes. So, no, it is not giving me everything that I wanted. But if that doesn't work, let me go to my emulation of Linux. Okay. So when I say give me the running programs, it says that you have only PS is running and bash is running, my shell. Okay. And it didn't give me much. But if I say give me all the information, give me all the information. Okay, it says, okay, first of all it says where I have started it, what kind of things I did, and my process ID. How about this one? Yeah, this one is better. This one in real time, every like 5 times a second, maybe 2 times a second, lists me all the programs that I am running, and it is giving me all that. This is the priority. About some virtualization, I don't remember what this is. Percent CPU I am using, percent memory I am using, what kind of CPU time I have used so far. Okay, so I get all that information. These are all the obtained from the process table. Process table has them. Okay, and each operating system has a way of keeping them, and it's an important part of the. Obviously, you cannot keep your process table very large. Part of the operating system, you don't want to keep that kind of information in the process table, and you keep your data when the process is blocked in your process table. If you lose that process table somehow, then your operating system has crashed. That's why it has to be. You have to be in the privileged mode to modify this process table. Maybe it is okay to read it, but definitely not modify it. Okay, good. Before I continue, I think I need to stop at this point because I am out of time. We will continue and we will finish up with chapter number one next week. Okay, that's it for today. I will see you next week.
Prosesin kaynaklarına mı bakmaya çalıştınız?
Efendim?
Az önce bir prosesin kaynaklarına mı bakmaya çalıştınız? Hani ne harcadığını, hangi thread'de ne kadar harcadığını vesaire. Kaynak
Yok, yani ne var orada onları göstermeye çalıştım. Niye sordun?
Yok hocam.